In this video, we're going to be working out a couple rotational kinematic questions where we have a bike with an angular acceleration of 4 radians per second squared. Let's go ahead and write that down. And an initial angular velocity of 1 radian per second. So omega I is 1 radian per second. And the first question we're answering is how far will it travel in 12 seconds if the radius of the tire is 40 centimeters? So I'm going to go ahead and label those couple variables as well. Time is 12 seconds. And then we'll put the radius down as 0.4 meters after we take that 40 centimeters and divide it by 100. So those are our set of variables to start off with. And we have initial question with how far it will travel. So we're looking for a horizontal distance, basically a delta x. So when we're talking about angular values, we're basically looking at s. So s is the arc length that's going to be covered for each of the tires, and the amount of arc length that's covered for each of the tires is going to roll the bike a certain amount. So the s is basically going to be like a delta x. So the first thing we're going to do is we're going to go ahead and find a delta theta, the change in the angle over the amount of time given. So we have delta theta equals omega I t plus 1/2 alpha t squared. So what we're going to do is we're going to use that formula in combination with this one. And after those two steps, we should be able to find our delta x from there. So after plugging in our values into these delta theta formula, we got 12 plus 288 radians, which equals 300 radians exactly. So that's how many radians are covered as the bike is rotating. And we used our second formula, s equals delta theta times our radius, to find our linear distance covered. As I said before, s is the arc length that is being completed by the tire, but as it rolls out that arc length along the road, that's going to be our horizontal distance, which ends up being 120 meters. So let's go ahead and solve the second part of our problem. It says, what is the angular acceleration if it then comes to a stop 4 seconds after the initial 12 seconds elapses? So let's go ahead and clear our initial work, and then let's solve the second problem. So what we're looking for the second one is we're looking for the new angular acceleration. So let's go ahead and cross this one out because that only applied to the first 12 seconds. And then it comes to a stop, so we know that the omega f is going to be 0. And then we still have the same radius, so we might be able to implement that. And then we are not going to use a time of 12 seconds anymore because it says it comes to a stop after 4 seconds. So with that, we do not have enough information yet. We need at least 3 variables for any kind of angular acceleration type problem. So if I'm looking at what we initially had, I would eventually be able to solve for the initial velocity. So I'm going to go ahead and do that. I'm going to take the angular acceleration of 4 equals omega final minus omega I over 12. Okay, and then with that setup, I can find the final angular velocity of the 12-second interval. And where that 12-second interval ends is where this one starts. So if I just cross multiply this 12, multiply both sides by 12, I got 48 plus that 1 is going to be 49. So I have 49 as my starting angular velocity for the second chunk of time. So it's going to go from 49 to 0, Now we can just implement this same formula right over here and use our new values and see what we get for our new alpha. All right, so after plugging in our values, we should end up with a negative value because we have something that's coming to a stop. So clearly it is going to be slowing down. So we're going to take our final minus initial, have a negative numerator, divide it by the time, and then we end up with a final answer of negative 12.25 radians per second squared. So I hope that was helpful in helping you set up and understand some angular kinematic problems. Thank you for watching and listening.